Welcome back. This is episode 7. This is on mantle convection. The real question we're asking is what drives plate tectonics? What causes seafloor spreading? What causes subduction to occur? What happens to those subducted plates once they get subducted? And then why do we get this differentiation in the crust? And so the mantle convection, why do the plates move around? Why do we break up supercontinents after so long? Those are all questions for today. And so it all has to deal with mantle convection cells. And so, welcome back. The first stop along this way, slide 2 here, this is from Scientific Reports in Nature London here. And that's a photograph from Iceland right there, where the Eurasian plate on one side is separating from the North American plate on the other side at a spreading center. So that's a spreading center. We've already kind of talked about those, so I'm not going to dwell on it too much. The Eurasian plate is on the right-hand side, and the North American plate's on the left-hand side here. They kind of look the same, don't they? Yeah, this is where the ocean kind of meets the land here. And if you recall, when we talked about hotspots briefly, I said that Iceland is probably one of those hotspots. And so here you can see what it looks like when you have a spreading center and a hotspot both. And so anyway, those are two plates breaking apart right there. You know, we haven't talked about it a lot, but I'm going to talk about it a little bit right now. And so that is, what do we get when we get to that subcrustal upper mantle that we talked about? We just briefly talked about what is the base of the crust and what defines it. So what defines the base of the crust is the moho. And so the moho is that discontinuity that's down below the crust. And so remember, continental crust is mostly granitic, maybe some igneous rocks in there, maybe some metamorphic rocks as well. And when you get to ocean crust, in fact, it's mostly what we said is mafic igneous rocks there. So what's below that and what actually generates the magmas for both of those situations where you get granitic magmas and you get basaltic magmas? Well, this is the rock type right here. That's a rock called peridotite. That image up here on the right-hand corner, those are a whole bunch of mantle xenoliths that they find in volcanic rocks. Pieces of the mantle that broke off from deep-seated volcanoes that bring that material up to the surface, and we can collect it right up here at the Earth's surface, which is kind of handy for us. We don't necessarily have to drill down to it like they did with the Joides resolution, right? And so, but that is a piece of a mantle right there, and it's a rock called peridotite. And so peridotite is the same thing as the mineral peridot, which is one of the month gemstones. I don't recall which one it is. Maybe it's I don't think it's September. I forget which month it is. But anyway, moho is the base of the crust, and it's based on a seismic discontinuity. And so he discovered that in 1909, Andrea Mohorovic. And so this is the discontinuity. And what he found was it's an increase in seismic velocity there. In 1928, it was Arthur Holmes who decided, it's like, what causes, the seafloor spreading. He didn't know about seafloor spreading so much, but they did know about like this idea of, in 1928, they already knew about the idea that Wegener had, right? So Wegener has said, this is all from continental drift. Arthur Holmes said, maybe if there is continental drift and what broke up those continents, it's not necessarily centrifugal force, it's probably something to do with the mantle. And so he proposed mantle convection cells all the way back in 1928, predating this idea of plate tectonics, but not predating the idea of continental drift. And so it took 7 decades to finally support that conjecture that he made. And it was in 1952, there was a guy named Francis Birch. He was a pioneer of mineral physics, and he showed that the mantle, we didn't know what was in the mantle at that time period, right? And he's the guy who did experiments in a lab and said, I think that the mantle is made out of this rock based on the seismic velocity that we see in the mantle. And so the peridotite, in fact, is what it is. So it's rich in iron and magnesium. And so he measured these high-pressure experiments to find out how fast seismic waves. So seismic waves are a lot like sound waves. So how fast do they go through different rock types? And so he's a person who did that. We still didn't know about plate tectonics yet at that time. And so people had proposed mantle convection because we knew that there was a core inside of the Earth. It was the 1920s, I think, that they found the core. It was Inga Lehmann who discovered the core, I think. And so she's a geophysicist and noticed that there were discontinuities not only in the upper mantle, but all the way, between the crust and the upper mantle. But in the middle of the mantle, there's another seismic discontinuity and several others beyond that, in fact. And so today we know that the lithosphere itself is made out of the crust, which is relatively thin, 10 in the ocean, 10 kilometers in the ocean, 70 kilometers on the continents. But the lithosphere itself can be up to 250 kilometers thick, right? And so those are the plates that move around, and they move around in what we say is a zone of partial melting. And so it's how do you describe it? Well, it's partly rock that's plastic that will move and flow, and it's partly molten material, and that's where many of the magmas actually get generated as well. So new crustal material comes from that same sort of interval right in there, where you get an intersection between the Earth's crust and this mobile mantle material, and new magmas can form it, for instance, ocean ridges, right, mid-ocean ridges. So if we looked inside of the Earth, you can actually see on the right-hand side here what have been the conjectured sort of versions of what a mantle cells look like, the convection cells. And so there's not a whole lot of dispute that there is convection in the mantle. And they've been able to image it kind of in certain ways. So that mantle convection cell is a lot like a boiling pot of water. And so these things actually rise up because they're heated on, superheated metal down there, right? So that metal is actually molten at the outer core right there. The inner core is solid, the outer core is molten. And if you can imagine what it's like being a rock on top of molten metal, okay, what's it going to do to the rock? It's going to melt it, right? And so, or at least heat it up, right? And so it's going to rise up, especially since it can flow. It flows plastically. And so it actually moves upward, and that's why you get the mid-ocean ridges in the centers of the oceans today. And then when you finally get out to where that rock cools down, the new crustal material gets over to the edges of these ocean basins, and you get subduction zones there. And so the subduction zones are where you get colder rock that then descends back into the mantle there. And at about 700 kilometers, that's about where the lower mantle kind of takes off, between 650 and 700 kilometers. And so there's a total different animal down there, sort of, from what we see in mantle xenoliths anyway. But we think it's mostly phase transitions between the kinds of minerals that are in the crust. And so once you get deep enough inside of the mantle, it goes to a type of rock called eclogite. And beyond eclogite, there are other types of mineral facies beyond that, but they typically have a lot of magnesium and iron in them. And so that is the idea of the flow cells over here on the right-hand side. On the left-hand side, that's the explanation at the top on the right-hand side over here. That's what most people think of when they look at the Earth, and they automatically assume from the coloration of what's in the mantle that the mantle is molten. It is not. And so it is not magma. There's a little tiny zone, of course, right, for that zone of partial melting, but that's pretty much it, unless you're sitting on top of a mantle plume. And in mantle plumes, you can actually get molten rock there, okay? But otherwise, you're going to have solid rock, but it's not hard solid. It's actually plastic solid. Silly putty is solid, but it can flow. So that's the way it is. Ice is a solid, but it too can flow when you get it into glaciers and things like that. You get it thick enough, it's going to flow. And so that's the way the mantle is, except the rate of flow is much, much, much slower in a mantle than in the mantle, as opposed to what it is in glaciers and things like that. And if I were to roll out a slender cylinder of silly putty and to put it at the edge of a desk, you would see that thing droop through the course of an hour, okay? So that's the type of way that material would flow, except even slower. Okay, so anyway, that's what most people think of when they think of the mantle. In that diagram on the left-hand side here, you can see the inner core, which is solid and glowing, that sort of yellow color. That's supposed to be molten metal outside of that, and that's going to be nickel and iron mostly in the outer core that's molten there. And so that is the light yellow there. And then beyond that, you can actually see the lower mantle in that sort of lightish orange there. And then the dark orange is going to be the upper mantle. And then finally you get to the base of the sublithospheric upper mantle there, and that's going to be the sort of brownish red color. That's what most people consider to be what's going on inside of the Earth. It's not that way. In this next slide, you can actually see what it probably looks like here. The Earth on the inside is probably mostly green, in fact, and so except where you get to the molten metal, and there it's going to be glowing red hot if you could get down there to see it. Which there's not going to be any color because color depends on light, right? And so there's not any light in there. It's all dark, right? But at the same time, it would be hot and glowing as though you took a piece of metal out of a forge, essentially. Except in this case, it's actually molten. It's molten iron and nickel. And so the inner core, in fact, would probably be glowing that same sort of orange color, but it wouldn't be a liquid. And so it's going to be a solid. So in this diagram, you can actually see the solid inner core here. I showed that in that sort of metallic gradient pattern there. And then outside of that is the molten outer core, which is hot in the center of it, right? Because it's right about as deep as you can go. And then once you get to the outer reaches of it, it's going to be pretty hot there. And molten, right? So these are all parts of this diagram. So I've just shown you the inner core, the outer core, and then above that there's a layer, and that's what they call the D double prime layer. And so the D double prime layer is what most people think is the graveyard of ancient subducted slabs. And so those ancient subducted slabs probably go all the way to the core-mantle boundary to that D double prime layer there. Now above that D double prime layer, there's probably a whole bunch of mantle convection cells. Now, and I've only drawn these sort of in with these sort of like bright green sort of like outlined arrows here just to show you that these things are kind of circulating inside of the mantle. A lot of folks who have studied mantle circulation based on the seismology think that many of these convection cells could actually be partly in the upper mantle. Some of them may be wholly in the upper mantle. Some of them may be in the lower mantle only. But anyway, they are circulating down there based on the heat that they gather from just above that D double prime layer. You heat it up. And so sometimes that D double prime layer gets so hot you can actually turn it into molten material. And it turns into things like the mantle plume that you see on the left-hand side of this diagram. That's a mantle plume that gets all the way up there to it gets all the way up to that zone of partial melting there. And so that's what the orange dashed line represents, that zone of partial melting there. And so there's a little slightly greener layer below that, and that's going to be the asthenosphere. So the asthenosphere is in the upper mantle, but it's at the top of the asthenosphere where you actually get that sort of zone of partial melting. And above that zone of partial melting, well, that's your scum. That is where the subcrustal upper mantle begins and goes all the way to the base of the crust, all the way to the moho, right? And so the crust on here is actually shown in two different colors. The black is supposed to represent the ocean crust, and the more brown sort of colors on here are supposed to represent the continental crust here. And so you can see very many different layers in here. So you get a very subtle change between the lighter green that's in the subcrustal upper mantle, a slightly darker green when you get into the asthenosphere. And then below that, when you finally get 650 kilometers inside of the Earth, you get into that lower mantle there, and that's that gradient sort of green color there. And then finally you get down there to that D double prime layer, which I still colored green in this issue. Okay, yes, I made this diagram just because I don't want people to think that the mantle is molten. Only the outer core is molten, and then some of these other features like mantle plumes And then the zone of partial melting has a little bit of melting in it as well. And I show a little bit of that sort of like indication for the mid-ocean ridges. So if you look at the black outline crust at the top of this image, and then over here at about 4 o'clock, as you were to go around on a clock face here, there's orange blobs in there. And so that's going to be the areas where you get seafloor spreading and you get new crustal material added with magmas there. And so that's all the different layers in here. So we've gone through them all, right? The mantle convection cell. Oh, yeah, in the outer part out here, there's actually a fuzzy sort of like gray layer on the outside. That's about how thick the atmosphere is. Actually, it's even thinner than that. But it is that sort of like bit on the outside there that is a bit fuzzy and kind of grayish or bluish, if you want to call it that. But anyway, I had to make this diagram just to show you that it's not like the textbooks show. I think it's more accurate, frankly. And so anyway, convection cells are those green arrows. And so if you heat it up at the bottom, like on a stove, like you put a pan on the stove, it's going to boil upwards, right? Usually it rises in the middle, and then it gets out to the edge of the pan, cools at the edge of the pan, and then descends down to the bottom once again. And so it rolls. It goes into a rolling boil, they call it, right? Well, the mantle's not a boiling it's not a rolling boil. Sorry, if I can get that out of my larynx here. It is not a rolling boil. It is in fact material that gets heated up and goes into a convection cell. Now, many of you may be familiar with ovens, right? And so ovens you can get a convection oven, right? What it does, it circulates the heat in that oven and it makes things cook faster, right? So everybody wants a convection oven when it's time for Thanksgiving, and if you're cooking a turkey in the oven or something like that, you want a convection oven because it cooks it longer. It cooks it faster, let me put it that way. You don't have to cook it as long, so you don't use as much energy in order to cook your turkey or whatever you're cooking in a convection oven, because they have a fan in them, and that fan actually circulates everything. In this case, the mantle's circulating all on its own here. It's a way of heat distribution, right? Okay, I didn't put this in the lecture, but just so that you know it, there's 3 types of heat transfer. And so one of them is radiation. And so one of them, you can actually feel infrared on your skin when you're out in the sun. And you can actually feel the sun's rays on your skin. You're a very good receptor for radiation, feeling the radiation, in fact, with your nerve cells and say, oh, it's hot out here today. And so that's one type of radiation is one type of heat transfer from 93 million miles away. That heat is reaching you from the sun in the form of ultraviolet and infrared radiation. And it puts out a spectrum of visible light as well, and it also puts out things like radio waves and probably a few X-rays as well. But anyway, we try to keep away from those as we can, and the Earth is actually protecting us from some of that with the Van Allen belt in the outer part of Earth's exo-atmosphere, if you want, or the outer parts of the Earth. There's a sort of like a deflection sort of thing that we have out there that keeps us from getting X-rays too much. So anyway, we have all of that going on. One type of transfer being radiation. The other one is conduction. That's where you put your finger on a hot stove and you feel it immediately. That's conduction. You've got a hot thing and a cool thing, your finger, and you immediately draw your finger off of it because you're having heat conducted to your finger, and you'll burn yourself. The other one, of course, is convection. So those are the 3 types of heat transfer. So anyway, when we talk about magmas and lavas and things like that, you get them in the spreading centers, and you also get them at the hot spots, right? So the hot spots will give us things like, well, Yellowstone National Park, right? There's a hot spot under Yellowstone, and you get a lot of heat flow there, right? And so, and then the other, of course, is the Hawaiian Islands, right? And so there's a handful of other places, right, that on Earth where you get that sort of activity. So I like to use analogies when I teach a lot. And so what I did is I bought an avocado, and I said, the Earth resembles an avocado in some ways, where the seed of that avocado is the core. Oh, okay, the core of an avocado is not molten, okay, which it wouldn't be very fun to eat if it were, right? But it's the core, right? So you can imagine if it were molten, it would heat up the rest of that avocado that's surrounding it, right? Most avocados, the parts that we eat anyway, are the green areas in there. And the crustal areas would be like the black areas on the outside on the skin, right? And so, okay, this was not a real good avocado here, but I ate it anyway. You take the seed out, you use that knife, smack it into that seed, twist a little bit, and you can pull the seed right out, and then you use a spoon and use the skin of the avocado as though it were a bowl and eat it right out of its shell that way. Anyway, that's what the mantle kind of looks like. It's got that same sort of green color there. And so that's why I wanted to give you that illustration and that sort of analogy. Okay, so when we talk about these things, we also want to talk about those hot spots a little bit more in detail. We've already talked about the seafloor spreading areas, right, and the mid-ocean ridges and so forth. And sometimes the hot spots coincide with that. It does when you get to places like the Galapagos Islands, and the same thing when you get to Iceland, right? But it isn't always that way. So sometimes hot spots can show up in the middle of a plate, like the Hawaiian Islands that show up in the middle of the Pacific plate, right? So that's a hot spot underneath the big island today. So that is an illustration over here on the right-hand side that shows you where the outer core is. Now, they kind of flatten it out there just because they didn't want to show you the rounded nature of that outer core. But you heat that material up in the D double prime layer, that material will rise up, kind of like a mushroom almost, kind of like a lava lamp. I think I made that analogy previously too. So the heat rises up, it gets up to that hot spot, and then it heats up that area, that hot spot, and causes magmas to then break through the lithosphere there and to get flood basalts, they call them. And so flood basalts are just massive outpourings of lava. And in this case, it's going to be an ocean sort of setting here likely. So that's what people think that the Hawaiian Islands kind of look like. And so that's going to be basalt in the Hawaiian Islands. And you can see the eruptions of some of that magma that's made it all the way through the crust and then erupting right there at the Earth's surface. And so this is on the edge of a place called Kilauea Caldera here. And you can see all of the people that are lined up along the horizon there. A very clever photographer took this image here, and you can see the outline of the people. They're not worried about being hit by that volcanic eruption. It's too far away. It's probably about a mile away, maybe 2/3 of a mile away, something like that. Now, they might smell the smoke, which is very sulfur rich, and they may get steam and things like that, but not a lot of it. And so, but that is a fountain eruption that's going off in Kilauea Caldera right there. And so, I mean, these people are so not worried about the eruptions there that they built a hotel right on the edge of Kilauea Caldera. And then they built the Hawaii Volcanic Observatory, a government building on the edge of that caldera as well. And so a caldera is essentially like a cauldron, right? And so it's the place where all the cooking occurs. And so Native Hawaiians actually revere this place as well. Of course, this is where the goddess Pele lives. And so there's a crater within a crater here. And oftentimes that second crater within the crater, the inner crater, will fill up with lava, and then sometimes it just drains out. And then sometimes it fills up and then spills over. But typically it's going to be there. So usually it drains out of the same feature that it fills up at some point. And that place is called Halemaumau. So Halemaumau is in the center of Kilauea Caldera there. Not all of the eruptions in Hawaii occur in Kilauea. Some of them occur along rift zones that run east and west, or kind of southwest from Kilauea Caldera. And then sometimes you get eruptions all the way at the very top of Mauna Loa, which is the giant mountain that's right next to Kilauea here. Kilauea is on the southern margin of Mauna Loa, and Mauna Loa is Hawaiian for Long Mountain. Anyway, these are the sort of rocks that you can get, right? And so there are different kinds of rocks that you get from these basalts. And that's one of the things I wanted to point out to you. So that's something that most, introductory geology courses don't point out. You already know that you can get basalts at mid-ocean ridges. You also know that you can get basalt at subduction zones. And you also get basalts at places like these hot spots, like in Hawaii here. And so they have 3 different acronyms for these things. And so I just wanted to share those with you because I think it's kind of neat. So the ones at the mid-ocean ridges, it stands for MORB, MORBs. So MORBs are mid-ocean ridge basalts. YABs or EABs are island arc basalts. So that's going to be in places like Japan, where you have an island arc that's erupting because you're subducting the Pacific plate underneath the North American plate there. And so that's an EAB or IAB. And then OIBs. OIBs are where you get ocean island basalts, and that's what you find in places like Hawaii. And you also find it actually, as I had to look it up, but you mostly get OIBs even in places underneath continents where you have hotspots. So even Yellowstone has OIB magmas. And so when it erupts, it's going to have the same chemical signature as an OIB. And people who are more into the geochemistry of basalts than I am know the difference of these things based on the sort of elements that are within them. So I guess it's titanium is one of the elements that they try to track to see if it shows up. And so there are different types of titanium, or at least different quantities of titanium that show up with these things. And so those are all the three different types of basalts there. And so I'm going to show you some of them here. Here's a lava over here. That's Nancy's finger pointing to a lava that is, it looks like it could be in Hawaii, but it's actually from Idaho. You know, if Yellowstone is where it's located today, it wasn't always there. The North American plate is moving over that hotspot, and what happens is that hotspot appears to migrate, but in fact, it's just the plate migrating over the top, heating up certain areas, and then you get effusive volcanic eruptions in that sort of setting. And so in Yellowstone, you get the OIBs that erupt there, right? Well, that's what you see on the right-hand side over here. A couple things to explain to you. The one on the left-hand side from Mountains of the Moon National Monument in that big valley that runs across southern Idaho there. That valley is called the Snake River Plain, and it's an area that tracks where the hotspot used to be millions of years ago, and not that many millions of years ago at Mountains of the Moon. But the hotspot track itself is like 12 million years, or 16 million years. And so you can actually track it across southern Idaho. You can track it into southern Washington state. So the track of the Yellowstone hotspot, that is. And so the hotspot's not moving, but the continent's moving over the top. So that is Pahoehoe over here on the left. And so Pahoehoe just describes the shape of the lava. It means ropey lava. And so that's some ropey lava over here. The alternative to that, and you see it sometimes in Hawaii, it's called A'a lava. And so A'a lava tends to be very blocky. And if you can imagine this, when you see ropey lava like that, what it means, it flows out pretty rapidly. When you have A'a lava, it tumbles essentially out of the volcano. And A'a lavas tend to be a lot more viscous. And so viscous refers to something that is resistant to flow. And so viscosity, the more viscous something is, the less likely it is to flow. And so Pahoehoe is less viscous than A'a, in other words. Over on the right-hand side, I told you already that is from Yellowstone. That's my old Tiguan right there. There's two sets, in fact, of columnar joints in here. So you can see the sort of polygonal shape, and many of those things are at the base of that cliff. And then above that, you see little tiny short ones in there. Those are called, they're called, let me get it right here. It's a polygonal fractures. And so these things are actually related to the cooling of magmas that would have been flowing out across this landscape. If they cool relatively rapidly, you're going to get small ones. If they cool relatively slowly, you'll get bigger ones. It's called columnar joining. And so columnar joining is what you see at the bottom, but also at the top here. And so cool rapidly on the upper part here, cool slower at the bottom part down there. And interestingly enough, this is the same sort of thing that you get at Devil's Tower. So at Devil's Tower, it's not so much basalt. It's a type of rock called phonolite. But in fact, you get columnar joining there as well. You can even get columnar joining with felsic magmas. And so even with things like if you have a rhyolite composition, you can actually get columnar joining in it as well. So it's really just a cooling phenomenon. So if you cool it rapidly, you form small ones. If you cool it slowly you're going to get the larger columns like at the bottom of this thing. If you've never gone to Yellowstone, make sure you make it there. It is one of the most beautiful places on Earth. So in this next image here, you can actually see that track. And so that track runs across and dates back about, I think it's actually 13 or 14 million years ago at the beginning of that. And so that's right at near the state line boundary between Idaho and eastern Oregon there. So yeah, I was off a state in that actually. So it starts in Oregon and then runs all the way into Wyoming, all the way through southern Idaho there. But that is the track of the Yellowstone hotspot right there. And where the magmatic activity is occurring today is pretty much where that red asterisk is there. And so we have overrun that hotspot with the North American plate. And so in the future, that hotspot likely will migrate even farther to the northeast there. So that tends to be the trend right now for the North American plate, heading to the southwest. So anyway, that tells you a little bit about that hotspot and how it's been stationary while the plate has been moving over the top of it here. And we can age date these things as well. So, so we know a little bit about that hotspot track right there. So how do we know anything about the mantle? Well, you've already seen mantle xenoliths. So, if many of the magmas actually come out of the mantle originally, people wanted to figure out, well, hey, can we drill all the way down there? And so the Russians actually did that. And so they actually drilled on the island of Sakhalin, which is in between mainland Russia and Japan. On Sakhalin, they actually drilled a very deep hole. And so they actually built a building around it because it's winter-like conditions almost all year round in Sakhalin Island. And so they built a drill rig there, and they drilled down 40,000 feet. That happened in 1989, just before the collapse of the Soviet Union, in fact. And so they drilled down, and when they drilled, they got all the way into Gabbro, and then they had to stop because every time they would try to drill deeper, the rocks were so plastic that they would move in and pinch the drill bit. And so they had real difficulties in trying to drill through rock that has a tendency to move a little bit at great depth. So how do we know what's inside of the earth? We can do deep drilling like that. We've also had mines that go pretty deep as well, so I'll show you that in a second here. And then we also do seismic imaging, and so that's what you see over here on the right-hand side. When we get into earthquakes, we're going to dwell with this a little bit longer here, but there's two types of seismic waves. They're called P waves and S waves. And they go through the entire Earth. So when you have a massive enough earthquake, it actually generates sound waves. Those sound waves can travel through the Earth. Some of them travel in a straight line. Those are called longitudinal waves. The ones that don't travel in a straight line tend to go from side to side. And so when they go from side to side, it takes longer for them to arrive there. And so we can tell all sorts of things about the layers of Earth based on the behavior of these waves through a solid medium, which is the mantle, and also through the inner core, as it turns out as well. And so when things finally hit the liquid outer core, or that fluid material that's in the outer core, that molten metal, it actually stops the S waves. So the S waves get to that sort of interface and stop, and they actually go through a conversion into P waves. And so the P waves keep on going. And so the P waves show up all the way on the opposite side, on the antinodal side from a seismic event. And so you don't feel P waves in this one sort of area. There's like a ring that goes around the Earth where you don't feel P waves when you have a massive enough earthquake. That's called a shadow zone. And so the P wave shadow zone is where you don't feel P waves. If you're, over 105 degrees away. So if an earthquake occurs at 0 degrees, if you go 105 degrees away from that on the globe, in a circular sort of way, right? So if you're going all the way around the globe at about 105 all the way out to about 145, it gets that sort of like a silent area in there where you're not going to record seismic activity. That's called the P wave shadow zone. The S wave shadow zone, on the other hand, because S waves can't travel through the liquid outer core, they are blocked entirely right at that 105 degree distance away from a seismic event. And so it's kind of bowl-shaped because of that, and so it's not ring-shaped. So P-wave shadow zone is going to be ring-shaped. The S-wave shadow zone is going to be bowl-shaped. And so, so seismic is one way we can tell what's inside of the Earth. And then the velocities help us to map the different layers within the mantle. And so we call those shifts in some sort of seismic velocity. We call those discontinuities. Okay, as we go on, we can have deep mines as well. I'm going to show you that in a second here. And then we can also do experiments in the lab, and they use what they call the diamond anvil cell. They have one of these at Carleton College, in fact. And so, and in fact, that's the ones I'm going to show you that we're getting to here. So diamond anvil cells, you can take in between two diamonds that are faceted, you can put a substance in there and then keep a lot of pressure on it. So you pressurize it and heat it up, and we can try to mimic the sort of heat and pressure that's in the mantle. And when you do that, you can take one mineral and turn it into other minerals under heat and pressure. That's when I was talking about phase transition within the mantle. So you can go from things like peridotite to eclogite. That's a phase transition. And there's other ones in there as well. So I'm not familiar with all the various minerals that are making up the mantle, but those are a couple that I'm familiar with. And then lastly, on Earth, we get to collect meteorites. And so meteorites come in from outer space, and many of them come from the asteroid belt. And so we're pretty sure in our scientific investigations that we've shown that the asteroid belt, in fact, was a former planet that broke up. We get things that are called stony iron meteorites. We get nickel iron meteorites. And so between the two of them, you typically get a lot more stony iron meteorites than you get nickel iron meteorites. But both of them come to Earth, okay? So they get perturbed by, some other celestial body that gets too close or whatever, and sends these things into what we call Earth-crossing orbits. And so these Earth-crossing orbits, every once in a while, Earth will sweep them up. Fortunately, we have a big sister planet out there that sweeps up most of them, and that's Jupiter and Saturn, right? So those are sweeping up meteorites like crazy out there. Lucky for us. Otherwise, we'd have a cratered surface on this, much more cratered surface than we have today. Today, we've only got a record of about 200 meteorite strikes on the planet today. But in fact, for the ancient past, there would have been a lot more. It's just that we have plate tectonics, and we also have a lot of erosion on this planet. We have an atmosphere, right? And so these things tend to break down very, very rapidly. And so meteorites don't last very long on the Earth, and neither do the products that they make, like the craters, right? But the moon, on the other hand, doesn't have any sort of atmosphere, and so it's been pelted by meteorites over the 4 billion years that it's been around, 4.5 billion years. Almost 4.5 billion years anyway. So we have a record of meteorite impacts on Earth. And so if you look at the meteorites up close, you can find out what type of composition they're made out of. And we're pretty sure that a lot of them are actually part of what was that ancient planet's mantle material. And then we're pretty sure that the molten part, the parts that were metallic, were likely parts of the interior of that planet after that planet had gone through something called differentiation, where the heavy things go to the middle and the lighter things float on the top. That's called differentiation. And so you get mantle floating on things that are much more dense. And so even in Earth's crust, the mantle is much, much less dense than what the core is. And so the mantle's always going to float on the things that are much more dense, which would be the metals that are down below it. So that is the deep well site there for it's the Kola Super Deep Borehole, and that's on Sakhalin Island there. If you wanted to go see the deepest mine on Earth, you'd have to go to South Africa. And so that's in Witwatersrand in South Africa. And ironically, Witwatersrand is a meteorite impact structure. It's about 300 kilometers across. But what it did, it probably weakened some zones. When that impact occurred, there's no gold that we know of in most meteorites. And so, in fact, what you get instead are weaknesses in the crust, and the gold will actually make its way out as a hydrothermal sort of deposit very commonly from these sort of fractures in the crust. And so this is one of the most rich gold mines on Earth. And so at this facility, it's 13,780 feet deep there. This is a diamond anvil press or diamond anvil cell right here. And so that sort of disc you see in the middle there is something to keep the material in between the two flat spots that are at the ends of both of the diamonds that you see here. So there's a diamond at the bottom, diamond at the top, and then you apply pressure to it. And then they shoot x-rays through it as well, and so they have it under an immense amount of pressure, and so that little disc that's in through the middle of there, that's the part that's labeled as a rhenium metal gasket right there. And so that keeps the pressure confined within that sort of space in there, and they put the sample in there, pressurize it, and see if it changes to some other sort of crystallographic direction. And so they put x-rays through it, in fact, because you get something called x-ray diffraction in this sort of technique. And what it does, it actually splits the x-rays, and from the peak, the characteristic peaks that you get in those x-rays, you can determine what kind of material it is, what kind of mineral it is in this case. And so that's a diamond anvil cell right there. Okay, and so the last image here is the different kinds of meteorites that you can get. So a couple of these, in fact. So we talked about, well, actually there's stony meteorites, and then there's stony iron meteorites, and then there's iron meteorites. There's actually 3 different varieties. So the stony iron, the stony meteorites are the ones that were mantle in composition. But every once in a while you see ones like this. Now that's a palisite right there. And so palisites are actually what people think is right at the core-mantle boundary. So if you wondered what the D double prime layer, it's probably something that's very similar to something like that. Okay, so you have the metallic contribution from the outer core, and then you have the rock contribution from the mantle of that ancient planet, and then when it breaks apart, and so some of these asteroids people think have crashed into one another, and when they do that, there's a strewed field of all sorts of material that would be out there, and some of those, of course, go into orbit around the sun and so forth, and so some of those actually cross Earth's orbit every once in a while, and so we can pick up meteorites like this, like the palisites. They're one of the most rare meteorites, in fact, on Earth, and so you can see those things, and people trade in these things all the time, and so they're worth a lot of money, in fact, and so the palisites are very collectible. So you can see what they do here, right, is you very thinly slice a palisite like that, and then you project the light through it, and so you can actually see the peridot or the peridotite, I think it's mostly peridot in this case, through that the metallic material that forms the interstitial material between the crystals there. And so what you see here, in fact, the metal itself is actually taenite and camosite, I think it is. So taenite and camosite are the minerals that form the matrix here. Those metals are like essentially the same thing as stainless steel, because you get iron, you get nickel, and in combination, that's what you use to make stainless steel. And that's what you see on the right-hand side over here as well. And so that's a nickel iron meteorite over there. Now, you see that pattern in there? It does occur naturally, but you don't see it naturally when you slice nickel iron meteorites. What they do, in fact, is they actually etch it with hydrofluoric acid in order to get those things to pop out, essentially. So those lines in there actually record the crystallographic growth pattern of these things as they went from a molten iron and nickel combination, and they slowly crystallized. And a lot of people think it takes millions of years. That's a pattern right there that we've never been able to duplicate in an experimental lab. And so that's called Widmanstätten structure here. And so that's a nickel iron meteorite there. And so the palisites, the stony iron, I didn't have a photograph of a stony meteorite on here, but if you look up Northwest Africa, you'll find a lot of Northwest Africa meteorites, in fact, are stony meteorites. Okay, to get down to the very bottom down here, that's an impact structure right there. That's called Beringer crater. The Beringer family first found that actually back in the early 1900s, and so I can't recall the gentleman's name who found it, but he was a mining engineer, and he thought, wow, it'd be kind of neat if this is really an impact crater, I should be able to find nickel and iron associated with it. And so he drilled all through that thing, couldn't find anything. Maybe just traces of nickel in it, and along comes somebody from back east, back in Kansas, actually. We think of that as being the west here, but for him it was back east. And his name was Harvey Neininger. And Harvey Neininger comes out here and he says, you mind if I look around the crater out here to look for meteorites? And Harvey Neininger found meteorites out there. And so I don't think the Beringer family was very happy about that situation. But in fact, today the Beringer family is enormously philanthropic. They actually give a lot of research money to people who study meteorite impact structures. And so the Beringer meteorite crater, it's known as Meteor Crater today. And so it's a visitors center. And so it's not a national monument, in fact. And so it's a private park. And it's spectacular, I have to tell you. You know, if it were a national park, it would have all sorts of problems, I think. But because it's private property, you know, those problems don't occur here because they can put their foot down and say, you can't do this or you can do this. And so they built this structure over here, actually, that was a very famous architect who built the visitor center here. And so, so they have this great philanthropic sort of attitude and make it wonderful for all their visitors. And so you realize today, you're in this class, right? You're studying geology, right? Do you know that we could have a meteorite impact tomorrow, right? And it could, like, you know, wipe out a city for all we know. Now, we do track these things. There are actually programs in NASA that are designed to track meteors in outer meteoroids, let me put it that way, and asteroids as well. Things that are 1 kilometer or larger. And then they also track smaller ones these days because the instrumentation's becoming easier and easier to get high resolution imagery out in outer space, you know. And so we like to track these things and try to figure out where their orbits go, and we find out if we're going to be at risk or not because we can model what the trajectories are for these orbits. And so there is supposed to be one probably towards the end of the 2020s here that poses a risk, but it's not that high a risk, and they're always constantly recalculating what the orbits of these things are, so that we're not in imminent danger right now. But it's like playing Russian roulette with a pistol that has a cylinder on it that has millions of empty slots to put the shells in, and only one of those has a bullet, and you spin it and you spin it and you spin it, and eventually you're going to hit that chamber and you're going to lose. So it's not real good, you know. It's not real good to see what happens when you are going to have a meteorite impact structure. You're going to wind up with something like this. Now, people think that the meteor that actually struck in Beringer Crater here, they think it was about 40 meters across. It wasn't very big at all. 40 meters is like the size of a small building, right? So even smaller than maybe a house. Okay, so maybe a little bit larger than a house, but not much. And it left this crater that's 1.1 kilometers across and 300, almost 300 meters deep. It's filled in with some sediment since then, and so the sediment washes in. It blew up, and so it came from the northeast and came in at about a 45 degree angle and left this giant hole behind. So that's one of the things I get to study, and it's like I love studying these things, and so I feel like I have a purpose in my life because I study meteorite impact structures. They're the most amazing sort of things. And so this is all about how we know what's inside of the Earth. We know it from diamond anvil cells. We know it from the meteorites and the various amounts that we have of each one. We know it from mantle xenoliths, and then we also know it from seismic evidence. And then, even in the deepest drilling that we've done, and we have drilled into the mantle now, but that was all serpentinite that they found in the mid-ocean ridges. And then when you get, too deep, you're not going to be able to drill. And so you can only go so far with a deep mine as well. I wanted to tell you, actually, in that deep mine that's in South Africa, the temperatures are like 135 degrees. It's about the limit of what humans can actually stand for any length of time. So anyway, that is the story of how we get understanding about what the interior of the Earth is like, what the mantle is like, and where the magmas are generated from. They're generated from subduction zones, they're generated at mid-ocean ridges, and they're generated at mantle plumes. And so those are morbs, yabs, and oibs. So those are the three varieties right there. I'm gonna call it right there. That's enough for now. So I will see you on the flip side. So next, we're gonna move on with part 2 of this course, which will be more into some what are minerals and what are rocks made out of. And so we'll get through the minerals and the rocks, and then we'll talk about the various structures that they make and how they all come together to give us the earth that we all have come to know and love. Anyway, thanks for your attention. I'll see you on the flip side. Bye for now.